My name is Dewan Lightfoot. I am a developer advocate here at AWS focused on cloud networking. The title of this session is A Developer's Guide to Cloud Networking. Now, I understand we all come from different backgrounds. I myself, I'm a network engineer. So if you start talking network, to me, as far as IP addressing, routing, security, VPCs, I understand that. But as a developer, you just want to develop your applications and they kind of work, right? You don't really want the network to get in your way. So my goal in this talk, whether you're a developer, you're an engineer, or you're an architect, is to just simplify things and talk about cloud networking on AWS. So let's kind of get started. This is a 200-level session. So what does that mean? We expect you to have some fundamental knowledge of networking concepts like IP addressing, CIDR notation, and security. This is also an interactive session, so I'll have polls, a couple polls throughout this session where you can kind of join in, answer the questions, and we can see how we all can interact and engage and, talk about some of the things we are experiencing in our infrastructures. Now, today's session, we're going to begin with discussing the AWS global infrastructure. Then we'll move on and talk about some of the Amazon VPC and security basics. Then we'll talk about connecting to your VPCs and your resources in your VPCs. And then after that, we'll talk about hybrid connectivity, like how do we connect from our data centers to AWS. And then finally is how do we get visibility into our networks on AWS. So for our first poll today, the question is, and you can pull out your phone, scan the QR code, and if everyone can do that, that'd be great. The question is, what percentage of your day, on average, is spent troubleshooting the network? Now, if you're a network engineer, of course, this is probably all day, or you're architecting or something. But if you're a developer, chances are you might not spend that much time troubleshooting the network. But if you're in a small shop and you're a developer and you kind of have to wear all hats, you may have to do that. So just kind of see where everybody's at, and we can discuss this. I'll give everyone a minute to complete the poll, and then we'll look at the results. All right, the results are in. So it looks like, ooh, nice. Less than 10% of your day is spent troubleshooting the network. That's awesome. You all have some amazing network engineers. That is beautiful. I love to see that. So thank you. Let's move on to our next slide. Okay, so the AWS global infrastructure. When we talk about deploying our applications on AWS, we have 32 regions. What does that mean? Well, these 32 regions all across the globe is where you're going to deploy your application, usually as close to your customers as possible. Within those regions, we have something called availability zones. We have 102 availability zones. These are where we cluster data centers, and I'll talk more about this in a moment. And then finally, we have 600 plus points of presence. Those are where you find CloudFront, cloud content delivery networks, as well as Route 53 and Global Accelerator. Now, when we talk about regions, a region is just a geographical area around the world where we actually cluster those availability zones. Usually we have 3 availability zones in each region. So when we talk about availability zones, these are clustered data centers. We have one data center, sometimes more data centers that are all clustered together to provide fault tolerance and high availability. These availability zones, there are 3 in each region, at least. And in those availability zones, they are separated far enough apart just in case there's a flooding near that availability zone or some type of earthquake, the next availability zone will still have high availability. Now, building a VPC. I mentioned a region. A region is a geographical area. Here I have US East 1, which is in Virginia. When you log onto the console, you select a region. In that region is where your resources like your VPCs live. If you go to another region, your VPCs and your resources in that region will be totally different. Now, you select your region, then you create your VPC. That VPC will span the entire region. Within our region, I mentioned we have availability zones. So a VPC can span multiple availability zones, but it only lives in one region. And then from there, you create your subnets. Your subnets go in one availability zone and one availability zone only. You cannot move that subnet. If you need another subnet, you need to create an additional subnet in another availability zone. And then from there, you launch your virtual machines, or what we call EC2 instance, elastic compute cloud instances inside of those data centers, which is those availability zones that I mentioned. And now you have your networking and you have your high availability if you are leveraging multiple availability zones. That's the basis of how we architect a VPC on AWS. Now, when we talk about Amazon VPC and security basics, there's some things we need to know. So, Amazon Virtual Private Cloud. If we look at this, inside of a VPC, the VPC lives in a region. Inside of that VPC, you have your EC2 instances, your Lambda functions, your relational databases, and things like that you put inside of your VPC. Now, we recommend that you use private IP addressing inside of that VPC. Outside of your VPC, even within AWS, things like DynamoDB, Amazon DynamoDB, Amazon S3, these are using public IP addresses. So what does that mean? If we're trying to connect to our VPC from the internet, or from our VPC connect to S3, we need some way to do that. So from the internet, nothing can get into your VPC by default. And from your EC2 instances trying to connect to your public services, whether it's DynamoDB or S3, can't do that unless you configure it. So these is the fundamental principles. Your Amazon VPC is basically a high-level container that's secure by default. Here's where you configure all of your networking. So let's go ahead and do that. When you create a VPC in a region, you're going to start with the CIDR block. That CIDR block can be as large as a /16, which is 65,536 IP addresses, or as small as a /28, which is 16 IP addresses within one VPC. Here I have listed 2 availability zones. In US East 1, we have 6 availability zones, but to keep things simple, I'm only using 2. So once you create your VPC, now what do you do next? You create your subnets within that VPC. But before that, an additional thing that I want to talk about is that a VPC can have multiple address blocks. So if you are running Kubernetes workloads, or you have very large workloads within your VPC and you need additional address blocks, or let's say you didn't right-size your VPC and you need to add more addresses or CIDR blocks, you can do that up to 5 for IPv4 and IPv6. When it comes to IPv6, if you do an Amazon allocated IPv6, you will get one allocated from Amazon or AWS that's up to 5, and it will be a /56, but you can also bring your own IP. So now we talked about CIDR blocks. Let's talk about subnets. We have our IP addressing for our VPC. For our subnets, what we have here is we have the ability to create an IPv4 only subnet, as well as a dual stack. So that means that the subnet will have IPv4 and IPv6. You can also create an IPv6 only subnet. You cannot create an IPv6 only VPC, but you can create an IPv6 only subnet. So you can dual stack your VPCs. Once you create a subnet within one availability zone, from there, there's some things you need to know. There are 5 reserved IP addresses every time you create a subnet. So those reserved IP addresses are going to be your network address, which identifies the network for that subnet, your VPC router, which we'll talk about more about that here in a moment, as well as the Route 53 resolver. This is going to be for DNS within your VPC. And then there's one reserve. We reserve that here at AWS. And then finally, broadcast. So in a traditional network, when we talk about broadcast, well, that's how you communicate to all IP addresses on one network. In the cloud, that broadcast does not exist. So that's not something you actually have going on inside of your VPC. And in the case of IPv6, we have the same thing. Now I'm using the DB8 IPv6 range. This range here is for documentation purposes, so this is not something that's going to be routable. Now, once you create your subnets and you launch your instances inside of your subnets, at that point, your instances will have something called an ENI, or an elastic network interface. Think of it, this is like your network adapter for your instances. Your instances will get a IP address from that CIDR block within the subnet. Same for IPv6. Now, there's something interesting about this, and we'll talk about this here in a moment when it comes to instances, because if you are using a public IPv4 address to communicate on the internet, if you look at your instance, if you do a if config, you're just going to see the private IP address block for IPv4. But for IPv6, you're going to get what you call a global unique address for IPv6. Those are global unique routable IPv6 addresses. Now, although they're routable, there's some controls that you can have. So when we talk about subnets, so we can really dive into this, is that subnets on a traditional network, in order for these subnets to communicate, they need something called a router for different subnets to kind of communicate. But in a VPC, this is totally different. It doesn't operate like that, and I'll show you here in a moment what I mean. When we talk about routing, I have 4 subnets here. By default, inside of a VPC, all 4 of these subnets can communicate. There's something called a main route table for a VPC. Whenever you create a VPC, you get this main route table. This route table will have what you call a local route. The local route will be for IPv4 and IPv6. This local route is basically a router within the VPC. It's not one router, it's a collection of routers. But either way, it routes the traffic for all of your subnets within your VPC. It handles that for you. So there's nothing within your VPC that you have to do by default. Now, you can have multiple route tables in a VPC, but you can only have one subnet. A subnet can only be associated with one route table. So when we talk about subnets kind of being that security boundary for a VLAN, it's not like that in the cloud. You mainly control the subnets with routing. So here we have a local route. If we want our IPv4 subnets to communicate with the dual stack, it's going to use IPv4 here. And then from our IPv6 only subnet, it will be able to communicate via IPv6. And all of this is due to the local routes that are in the routing table. Now, we talked about the VPC, we talked about IP addressing, we also talked about subnetting, and we talked about routing. The next thing we need to talk about is security. Security in a subnet is a boundary on a traditional network. But in the cloud, the boundary for the subnet is going to be your network access control list. These are stateless firewalls, meaning that if a client wants to communicate with our instance, to SSH into that instance, we need to define a rule inbound. Traffic is allowed, so the request goes through. But we also need to define a rule outbound. And traffic is allowed. So this means that whenever you're creating a VPC, you create subnets, a subnet will go to the default network access control list is there. That default network access control list by default allows all traffic in both directions. If you want to manage controls at the subnet level, you can use network access control list. Normally your network team will put something broadly there to block IP addresses from specific ranges of addresses, but normally you're just going to leave this broad and just leave it as is because there's another way to control security within your VPC. Now, I mentioned this needs to be in both directions. Here, the inbound, we are allowing traffic, but on our outbound rule, we're denying traffic. So this means when traffic from our instance tries to reply to our client, it will be denied by default due to not having a rule on the outbound. So if we want to allow traffic from our client, we can add a specific rule allowing that traffic. On the inbound, we add the rule on the outbound. But then if you don't do this broadly, you'll have to do this every time for all IP addresses in your subnet. So like I mentioned, there's a better way to do this, and here's where we start talking about security groups. Security groups control our access to our instances. Here, we have a security group that's surrounded our instances, but in reality, it's actually protecting our ENIs, or our network interfaces within our instances. So if we remove our VPCs and we just focus here on our instance and our security group, how does it work? Well, security groups are stateful firewalls. That means if you put a rule in place on the inbound, the request and the reply will be allowed if you have a rule in place. So here we have a client that wants to SSH into our instance. It sends a request. the reply will be allowed. Now, what about the outbound? On the outbound, we put one on the inbound to allow traffic in. To allow traffic out of our instance, we can use outbound rules. Here we have an outbound rule allowing traffic to our web server. And again, the request is sent, and the reply will be allowed because it's a stateful firewall. And these protect our instances. So if you're trying to provide granular control to your instances or to your VPCs, you're going to do this with security groups. And I'm going to show you a way that we can even expand upon this. So we have one security group, one instance in our security group. What happens if we add another instance to that security group or another one? What we can actually do is reference our security group, because right now our instances can communicate via SSH because they have the same security group. But what happens if they want to ping or send an HTTP request between those instances? Well, because of this rule that we have in our security group, it won't be allowed. So what we could do, if we have some type of auto-scaling groups and we're using this in our deployments, what we could do is actually reference the security group itself. And then at that point, we're allowing all traffic between these instances that are in this same security group, and then traffic will be allowed. I kind of went too fast. There we go. Awesome. So here we have two security groups. We have a database server that's in our database tier and a web server that's in our web tier. Of course, we want our clients to be able to communicate with our web server, but we don't want our clients to communicate with our database server. So how can we manage this? Well, we have two security groups, one for the web server, the web tier, and one for our databases. We create a security group allowing traffic to access our web servers. Then we create a security group that allows our web server to access our database servers. But this time, rather than using an IP address, we referenced the web server's security group. So now we can reference other security groups. So this means that when the web server wants to communicate via port 3306 to the database tier, traffic will be allowed. And since we're referencing other security groups, if we're auto-scaling, each instance that is added to that security group will also be able to communicate with our database tier on the scale up and the scale down as well. Now, connectivity within AWS. I mentioned by default, when you try to connect to a VPC, either inbound or outbound, it's secure, right? So how do we get connectivity to the internet? Here we have instances in 4 different subnets. There are 3 things we need to do to provide connectivity from our instances in our subnets to the internet. The first thing we need to do is attach an internet gateway to our VPC. A VPC can have one internet gateway. An internet gateway can be attached to one VPC. This is what provides that internet connectivity for your VPCs. The next thing we need to do is your instances have to have a public IPv4 address or IPv6. Your internet gateway can handle traffic for IPv4 and IPv6. The third thing we need to do, we need to ensure that our route table has a route to the internet gateway. Now, if you're using IPv6, you have to add a rule for IPv4 and IPv6. This same thing applies for security groups and network access control lists. So if you're using dual stack subnets and you're using a dual stack VPC, when you're using security groups, route tables, you have to also think about IPv4 and IPv6 in those route tables if you have dual stack subnets. So here, at this point, our ENI for our instance in the subnet with the 10.0.1.0/24 has what you call EIP. These elastic IPs can be associated when you launch your instance, or you could associate an elastic IP after the fact. And so this would be like a static IP, a public IP that you will actually keep. So if your instance shuts down or restarts or anything, it'll have the same IP when it returns. Once we have all of these 3 things, at that point, your instances can communicate on the internet. Now, I mentioned previously about your IPv4 instances having private IP addresses. If you're on your instance, you do an if config on eth0, what you'll see is a private IP address. But we know that we have a public IP address. What we can do is send a query to the instance metadata service to find out what the public IP is that's attached to this instance is. And so this public IP is actually a one-to-one address translation via the internet gateway. So the internet gateway is doing some type of address translation of one-to-one for your instances at IPv4. But at IPv6, your instance will have an IPv6 address. Now I mentioned the IPv4 connecting to the internet. Here we have our public subnets that have a route table. Now, have you all heard the term public subnets, private subnets? Okay, let me explain this. So on AWS, if a route table has a route to an internet gateway, it is a public subnet. If it does not have a route to an internet gateway, it is a private subnet. Now, when we talk about connectivity via that means that our public subnets will send traffic via the internet gateway, and our private subnets will only be able to communicate locally within the VPC. They don't have a route. So I mentioned that we can have multiple route tables within our VPC. So now this is how we control some extra security within our VPC. So now we add our public subnets, we associate them with the public route table, and then we associate our private subnets with the private route table, and we manage routing at that layer to say what can communicate with what. And then we're also adding security with our security groups. And here we are communicating via the local route. Here we have 3 local routes because we have 2 IPv4 VPCs, IPv4 SATA blocks to our VPC. So moving on, connected to the internet. I mentioned public subnets and private subnets. The next thing I want to talk about is the NAT gateway. You may have your database tier that wants to communicate in the internet, to the internet. Well, we know that we don't want those access from the internet, from the public internet, and we don't want to put them in the public subnet. So what we can do is keep them in the private subnet, create an internet gateway in each of our availability zones because we don't want to send traffic across the availability zones because of the data transfer charges. And then at that point, we create a route table for each of our subnets in each availability zone, and then you point them to that NAT gateway in that availability zone. So now when our database servers need to communicate with the internet, they're going to leverage the route tables in that availability zone that's pointing to the NAT gateway. And since the NAT gateway does the network address translation, that's AWS managed, it's sending traffic to the internet gateway via the public route table. And so now when our instances in our private subnet want to communicate with the internet, they're going to go via the NAT gateway through the internet gateway to the internet. And so that means that our private subnets are protected. So if traffic wants to communicate with them from the internet, it will not be allowed.
About responses?
Oh, responses are allowed. As long as you have your network access control list configured correctly, responses will go through. Awesome. Now, we talked about IPv4, we talked about the NAT gateway. Now we need to talk about egress only, or IPv6, egress only internet gateway. So we may have workloads that are in our private subnets, and since they're using that GUA that's globally routable, what if we don't want our workloads to be globally routable? We don't want to route them on the internet. What we could do is create a routing table that does not have a route to an internet gateway. We attach a egress-only internet gateway, and then at that point, we put an IPv6 default route pointing to that egress-only internet gateway, and now traffic will go through the egress-only internet gateway, and if traffic tries to come from the internet, it will not be allowed. And so if you're running IPv6, there's no charge for the internet gateway or the egress-only internet gateway. So we talked about connecting to the internet. What about connecting from the internet? Well, here we have a user. Let's call that user Dewan. Dewan wants to connect from the internet. There's 5 things you need to do. The first thing, just like with access to the internet, you need a public IP on your instance. This is the public IP that you're going to use to communicate with that instance. The next thing you need to do, you need to ensure for that instance you have a security group that allows the traffic that you want to communicate to that instance. From there, you need to ensure that your subnet boundary, the network access control list, is allowing traffic to that subnet. From there, you need to attach an internet gateway so traffic is allowed into your VPC through the internet. And then finally, you need a route for your public subnet that points to the internet gateway. And so at that point, if I wanted to SSH into my instance, I could do that from my user Dewan. Great. Now at the beginning, I talked about this slide where you have your Amazon VPC services like your EC2 instances, then you have your public services that live outside of your VPC on AWS. How do you connect to those services? Privately. Well, one of the questions I get is VPC endpoints. What's the difference between a gateway endpoint and an interface endpoint? It's often a question I get. Well, the first difference is that when it comes to gateway endpoints, they provide private connectivity to AWS public services, but only 2 services, Amazon S3 and Amazon DynamoDB. The next difference is if you're connecting to work and you're transferring data to and from S3 from your VPC, you're going to use a gateway endpoint, and that's going to save on data transfer charges because there's no data transfer charges using a gateway endpoint when you're connecting from your VPC to S3. And then the third thing is when you create your gateway endpoint, you're going to have a route in your routing table that's a prefix list that has the IP addresses for Amazon S3 and DynamoDB. And then now when your instance wants to communicate via S3, it's going to go through that gateway endpoint because there's a route in the routing table that points to that gateway endpoint. And so this allows you to connect privately from your VPC without an internet gateway, without a NAT gateway, and without VPN. The next option is going to be interface endpoints. Interface endpoints are powered by Private Link, so it provides a private and secure connectivity between your VPCs and AWS services. So we have hundreds of services that you can leverage interface endpoints for, but essentially what it does is you create an interface endpoint, and then that interface endpoint creates an ENI within that availability zone, within that subnet, that looks like it's exactly in the CIDR block of your subnet. And so now when I want to communicate with CloudWatch, I'm going to communicate with that interface endpoint that's in my subnet, and I'll go to directly, privately, powered by Private Link to Amazon CloudWatch. So if you think about the differences between a gateway endpoint and an interface endpoint, just think about when it comes to gateway endpoints, I'm using a route in a routing table rather than the interface endpoint is powered by AWS Private Link. And I'm going to have an IP address or ENI that I can also use DNS to communicate with my services. Now, Private Link also gives us the ability to leverage our own services or customer services, or if we want to expose a service to another customer, but we don't want to have that bi-directional communication, we just want that unidirectional communication, what we could do is we use a network load balancer, we put our servers in a target group, and then from there, we can leverage Private Link for our consumers to be able to consume our services. So basically what we do is we use Private Link and we expose our service, and then now that service can be consumed by other consumers from other VPCs, other accounts. And this, again, is without a internet gateway, without a NAT gateway, as well as without VPN. Yes? Yes. is that it can privately go between regions, the network load balancer. Now, connecting between VPCs. There's a couple options to do that. The first is going to be VPC pairing. VPC pairing creates a one-to-one bidirectional communication between two VPCs. Think of this as a point-to-point communication. Now, every time you want to connect to another VPC, you got to create a new point-to-point communication. So that means you got to update routing, and you got to manage all these communication between these VPCs. So after you scale beyond a couple of VPCs, this becomes a challenge to manage. So if you want to centralize this, you're going to use the AWS Transit Gateway, which is going to be that hub and spoke technology, where the Transit Gateway is the central AWS centralized router or centralized hub to where you attach your VPCs, your VPNs to the Transit Gateway, and then at that point, you manage the routing between those VPCs centrally via the Transit Gateway. And we also talked about private links, so if we need to connect between VPCs in a unidirectional fashion, we can also use private link for that TCP communication. Now, some additional information about connecting between VPCs with Amazon VPC pairing. The max peers that you can have is 125 VPCs, but there is no bandwidth if you're using VPC pairing. It's also routed bidirectional connectivity. And then for the AWS Transit Gateway, you can have 5,000 VPC peer attachments to the VPC. And each one of those attachments per availability zone can have 100 gigabytes per attachment. And they're routed bidirectional as well through the Transit Gateway. And then finally, private link, there's no quota for the number of consumers that can consume your service. And it scales up to 100 gigabytes per second per ENI in availability zone. And this is also unidirectional. Now, we talked about connecting to your VPCs, we talked about connecting from your VPCs, and we also talked about connecting between VPCs. Let's talk about hybrid connectivity. If you want to connect from your data center to AWS, there's a couple options. The first option is going to be leveraging the VPN gateway. You attach a VPN gateway to one VPC. That VPN gateway can attach to one private gateway can attach to one VPC. And then from there, you use AWS site-to-site VPN to connect to that private gateway between your customer router or firewall. And then for each VPC, you create a new VPN connection. Now, if you need a more dedicated direct connection to AWS, here's where you're going to use Direct Connect. This is going to go through a Direct Connect partner, and then from there, you can use a Direct Connect gateway to connect your VPCs, and then you have connectivity from your on-premises to AWS, and if you want to provide high availability, you will have two Direct Connect connections to your Direct Connect gateway, which connects to your VPCs. Now, we can also leverage the Transit Gateway. So the Transit Gateway allows for VPN connections. So when we're using site-to-site VPN, we could actually connect directly to the Transit Gateway, as well as if we're using Direct Connect, we can leverage Direct Connect and connect directly to a Transit Gateway. So rather than managing multiple virtual private gateways, we manage everything centrally from the Transit Gateway. And again, if we need high availability, we create a second Direct Connect connection in a different location. Now, traffic monitoring and visibility. On AWS, there's a couple ways to do this. But before we do that, let's do a poll question. Since we only have about 10% of you that had to manage your networks, I would like to know, what's your biggest challenge when it comes to troubleshooting your network problems in the cloud? Awesome. Looks like the results are in, if we can see the results. Okay, we covered two of them, security groups and NACLs, as well as routing. Okay, so when it comes to traffic visibility options and use cases on AWS, there's two main options that we can use within our VPC. There's going to be Amazon VPC flow logs, as well as Amazon VPC traffic monitor. And we'll talk about both of those in a moment. Okay, with Amazon VPC flow logs, these allow you to get metadata, like source, destination, port, to be able to see, okay, what's communicating on your network? Who are my top talkers? You can take this data, you can send it to Amazon CloudWatch, or you can send it to S3. This helps you troubleshoot your network to get that visibility of your network patterns to understand actually what's actually traversing your network. These can be assigned at the ENI level, so if you want to get really granular to see what's communicating from your ENI, they can also go from a little more broadly at the subnet level. So if you want to capture everything that's coming out of your subnet to determine metadata at the subnet level, and if you want to go extremely broad, you can actually use VPC flow logs at the VPC level as well. Now, what if you want to do traffic inspection to see, okay, I see the metadata, but I really want to be able to look inside those packets and understand what's communicating on my network and the type of traffic that's actually traversing. So what we can use is Amazon VPC traffic mirroring. What this is you configure it on the ENI, and you're able to copy this to another ENI instance, gateway load balancer, or some other private third-party partner. So it takes the communication, and then once it has the communication coming into the instance that you assign that you want to traffic mirror, it takes a copy of that traffic, and then it sends it to the instance that you assign. The next tool we have, and I think this tool is really helpful because when you're using AWS, you're looking at your security groups to understand the actual security rules that you have in place. You have your NACLs in place, you have your firewalls in place, you have all these different areas you have to look. Well, we announced Reachability Analyzer, which basically looks at your network configuration and analyzes it to determine the path of that communication. For instance, if our instance can communicate from our instance to the internet, we can actually look at the entire path. So we know we start from our instance, then we go to our ENI, then we go out the ENI from our security group, then from there we go to our network access control list, then from there we go to our routing table, the internet gateway. It's looking at each hop. The thing is, it's not sending pings, it's actually looking at the configuration to determine, okay, what is your configuration and how should this actually intended path be? And so once it determines, oh, there's an issue with the routing table, at that point, it will give you notification to let you know exactly in your path where the problem may lie. So now you can troubleshoot it, add the route to the internet gateway, and be able to communicate with the internet. Reachability Analyzer is supported by instances, internet gateways, network interfaces, and a bunch of other source and destination resources and other intermediate components. You can learn more about this as well. So that completes today's presentation. My name is DeJuan Lightfoot. I thank you all for joining today. If you all have questions, I'm here for Q&A, and I will take some time to answer your question as well. So thank you all.